This video is about three standing wave problems, the sorts you're likely to get in an A2 exam, and they get harder as we go on. So here's the first one. We've got this graph here of displacement and distance. We've got to find the wavelength, mark A for an antinode. We also have to calculate the speed of these travelling waves in the medium that they're in, and the fundamental frequency of the apparatus. So, first things first. First thing is the wavelength. Now, as we know in standing waves, the wavelength is calculated as the distance between two nodes times 2. So in this case, it's 0.3 meters. You can mark for that. And any of these points here are antinodes. So there's our first two marks. Right, the next one, we've got to figure out the frequency. So you get 1 mark for using the wave equation, C equals F lambda or V equals F lambda, whichever one you want to use, and you end up with 10.8 meters. Now the fundamental frequency is the lowest frequency at which a standing wave will form. So this is the third harmonic because we have the first harmonic is 2 nodes, second harmonic is 3, and the third harmonic is 4 nodes. So we basically take 36 hertz, which is for the third harmonic, and divide it by 3 to find the fundamental frequency, which is 12 hertz, the first harmonic. Next question. We've got to describe, with the aid of a diagram, an experiment to describe stationary waves using microwaves. Then we have to measure the wavelength of these microwaves. So here's our diagram that we need to draw. We need a microwave transmitter, a receiver, and something for the microwaves to reflect off. So as we move the receiver between the reflector and the transmitter, we should detect nodes and antinodes. Now, we need our transmitter and a detector. We need something for the wavelengths, the waves to reflect off. Then as we move it between the transmitter and the reflector, that'll give you another mark. We get maxima and minima. So there's your 4 marks. Question B, we would detect, as we said, the nodes as we move the receiver along. One of the marks for experimental rigor here, just for taking many measurements between the nodes and then using our calculation to figure out the wavelength. Distance between 2 nodes times 2, we'll get you that last mark. They reflect off the bench, and as they come back, they'll be detected by the microphone. And basically what's happening here is the microphone has been moved up and down the clamp stand, and the oscilloscope gives you this mental looking graph here. So the frequency of the sound waves is 3.2 kilohertz, which is really high, ultrasound. We've got to determine the value for the speed of sound. So, easy enough, we can figure out the wavelengths from the graph. So you get any value, in the marking scheme you get any value between 5 and 5.6. The wavelength in a standing wave is 2 times the spacing between nodes or antinodes. So in this case, 5 and 5.6 would get us it. Using our wave equation speed calculation gives us 320 to 368 meters per second as a range. The contrast and the maximum and the minimum becomes less pronounced. So basically the question is asking for 2 marks. Why do we get this mental graph? So, as the sound waves move backwards and forwards, they interfere constructively and destructively. But the further you get away from the bench, the reflected waves are going to be weaker. So, they're going to lose energy. So, noise cancellation is less effective. The nodes become less pronounced.